Okay, calculates. Calculates, students who do calculus. Never heard that before. Just kind of made that up. So that would be you guys, though. All right. Let's see. Hope you're having a good week. We're going to do section 11.1, which is the beginning of differential equations. And then you're going to go from here, after we do this chapter, then 4B, which many of you guys are going to take next semester, is a course on differential equations. So this will get you set up for that. Once we're done with differential equations, which will take 2 to 3 weeks, we'll spend a week back on integration, just to make sure you're dialed in on that for when you take 4A, or multivariable calculus, and then get you ready for your final exam. So it's coming to a close. Lights at the end of the tunnel. So 11.1, I'm going to use the same examples in the book, because I'm just going to do a brief overview, and then that way if you want some more detail, you can go dig back in the book before class on next Monday or Monday after Thanksgiving. So your homework, though, is going to be 1 to 3, 5 to 9, 11 to 14, and 15. This section is pretty straightforward. It's just an intro. I'm going to give you some information without proof or explanation, and then we'll show where it comes from a little bit later. Okay, first of all, what is a differential equation? We've already done them, as you'll see. What is a differential equation? Okay, it's a question. The answer is an equation with a derivative. In it. And what is a derivative? A derivative is a rate of change. And I'm going to pause you because I've got a phone call here. There, sorry about that. Okay, derivative is a rate of change. So one of the ways that I like to think of it is, well, a few different ways. I took a fluids class, and if you think of this as a wing and the air, I think I've showed you this in class before. It cuts through the air, so the air is going this way, and the air on the top has to go a much longer distance than the air on the bottom. Okay, and so the rate of change of the air on the top is different than the rate of change of the air on the bottom. So we use derivatives to represent how fast the air is changing, because the rate of change of the air is changing as it goes over the top versus over the bottom. Okay, so that's just one quick little example. Another thing might be water flow through a pipe. It's not constant because of the friction and pipe roughness and things like that. Doesn't flow as fast along the edges. It flows faster down the middle. So the measure of how fast it's flowing can be modeled by a derivative, because a derivative, again, is a rate of change of the speed or flow of the water, and so forth. Okay, so let's look at a couple examples, and then that should get you going. Let's look at this example. Like I said before, it's in your book, but see if this makes sense to you. Suppose dy dt equals 100 minus y. Okay, so that's telling me, if you tell me what the y value is, I can tell you what the rate of change is. Okay, and y is a function of t, so if you tell me time, I can tell you what y is. And in particular, well, let's say for this equation, we have y is equal to 100 plus c e to the minus t. Again, how in the world do we get that? We're going to show you that later. This is just to give you a working understanding of differential equations at its most basic level, I suppose. Okay, so this right here for this equation, this is a solution. This is a solution. In other words, this right here makes this equation true. Okay, well, let's verify. Let's look at what is dy dt. That's equal to derivative of 100 is 0. This is going to be c e to the negative t times negative 1, right? Or negative c e to the negative t. So this is a derivative, so that's the left side. Okay, so I got negative c e to the negative t equals 100 minus y. Well, what's y? That's this right here. 100 plus c e to the negative t. Now, is this equation true? Question mark. Well, that becomes 100 minus 100 is 0, and it becomes negative c e to the negative t. And on this side I had c e to the negative t. So yes, these two are equal, so therefore this is in fact a solution. Now, does it matter what c is? And the answer is no. If c is 2, these two are equal. If c is 3, these two are equal. So what we have, this is not just a solution, this is what we call a general solution. A general solution because it works for all values of c. Okay, sometimes we also say this is a family of solutions. Okay, so it's a general solution, it's a family of solutions. Now, what about, let's go up here. What if I give you more information? What if I give you, say, what we call an initial value? Suppose I told you when t equals 0, y equals 0. Okay, so this is an initial value because it tells me what y is at the start, the initial time. Okay, well, if that happens, then I can use this to find c. Then from this equation here, I get 0 equals 100 plus c e to the negative 0. 0 equals 100 plus c, because e to the 0 is 1. So then c equals negative 100. So y equals 100 minus 100 e to the negative t is what we call a particular solution. Okay, to dy dt equals 100 minus y. Okay, so to recap, I have a differential equation. I've got general solutions. That's all of the solutions that make this true. And then if I give you an initial value, that allows me and you to find c and get a particular solution, which is a solution that satisfies some condition, which is our initial condition up here. Okay, so let's look at another example. Okay. We know that if I have the position function f of t, that if this is position at time t, then I know if I take the derivative ds dt, I get f prime of t Well, this is the rate of change of my position, which is my velocity. So that's velocity. And then I know if I take the derivative of velocity, dv dt, that's my change of velocity, which we call acceleration, which is the second derivative with respect to t. Okay, so let's go backwards now. Suppose I tell you I'm standing here on a cliff, and I'm going to take, I guess that's kind of a long arm there, right? Standing on the end of a cliff, and I throw a rock down. And the initial velocity is 10 meters per second down. And that happens when t is 0. Okay, well, I've got this rock sitting here, and I know that rock has gravity effect acting on it, so I know the acceleration is negative 9.8 meters per second squared, right? And that acceleration is the second derivative, oops, we can write it like this, second derivative the second derivative of my position, right? Now, if I take the integral of both sides, I get the first derivative, which is my velocity, which we mentioned. Well, if I integrate both sides, that's negative 9.8 t plus some constant. We'll call it c1. Right? So, if I take the derivative of this, I get back to where I started. Okay, so this is for sure a solution. Now, how do I find c? Or did I call it c1? I just erased it maybe. Sorry. Okay, well, we know that when t is 0, the initial velocity is 10 meters per second. So velocity is negative 10 because it's going down. We denoted negative to be the down direction. T is 0 plus c1. So c1 is negative 10. So then my velocity, which is ds dt, is negative 9.8 t minus 10. Okay, now let's go take an integral of both sides and solve this differential equation. Because this is saying, remember, the rate of change of my position is dependent on the time. It's changing. It's speeding up as it's going down. So if I integrate both sides and get s, I'm going to get negative 9.8 t squared over 2 minus 10t plus, call it c2. Okay. And if my cliff up here was 120 feet tall, then when t is 0, my position is 120. So I get negative 9.8 t squared over 2, oops, t is 0, minus 10 times 0 plus c2. Okay, so then therefore c2 is 120. So therefore my position is negative 9.8 t squared over 2 minus 10t plus 120. Okay, so here's a solution, a particular solution to this differential equation. This is called a first order differential equation. First order means it's the first derivative, and it's a particular solution for this second order differential equation. Okay, so we've got second order differential equations, first order, a particular solution, and we go from there. So looking at your homework, let's kind of take a look. I think I've got your homework on here. Okay, so if you look at this, we're asking things like, is this a solution? So plug that into here. Take the derivative for y prime and y, plug it in, see if it's true. Same thing, figure out if these are solutions. You're going to find dy dx and plug it in here and see if both sides are equal. Sometimes you have to plug the y into here too, right? Okay, so that's what we're doing. Show that this satisfies this differential equation. Okay, so here, find the particular solution given the, okay, so here's a general solution, and then they give you initial conditions. So when t is 0, x is 5, you can plug them into here to figure out what the constant is. Okay, so you should be good to go on this, I believe. So go ahead and give your best shot. I don't know where my assignment went. I know it's on here somewhere. I've got a whole bunch of stuff. Sorry about that. I just don't know where my work went. There we go. Okay, so we come back up here. So there's your homework. Do your best. Have a great Thanksgiving. Hope you all enjoy the week off. And come back ready to go for a good push to the end. Alright, we'll see you.